welcome once again in today's class. So we'll be continuing our discussion on metallocenes in polyolefin chemistry. Today's class will be little different from the rest of the classes. So far, what we have learned the development of the metallocenes in polymerations, and we have seen that metallocene is wonderful replacement of Ziegler-Natta catalysts for its reactivity, for its selectivity, and also we have learned that how to make this homogeneous metallocene based catalyst to a heterogeneous catalyst to make it industrially viable and to make it most cost effective. So till date we have discussed the use of the metallocenes in bond making process, that is the polymerization process, where we have seen that monomers can add to another monomer and making the polymers. Today we will discuss the depolymerization, that is the reverse, and you may ask that why we are discussing this one in this class, because it is a the title of this course is metallocenes based catalysts for polyolefin. It is important considering the time relevance and the environmental concern, and you will see at the end of the classes that how the metallocene, the same catalyst, can be used for polymerization as well as depolymerations. I will try to give the concept and try to understand by simple mechanism and simple concept or organometallic chemistry, and you will be really excited. I am very much sure to know that how this same catalyst can be used. But before starting, I want to mention that the concept is old. Okay, the organometallic chemistry of the transition metal complexes, but the use of these complexes for depolymerization, that is new. So you will not find much information in the textbook for this one. Obviously we will use the same unique reactions or organometallic chemistry, that is our textbook knowledge, but the particular uses of these organometallic compounds for depolymerization you will not get in textbook. So we will use some very recent reviews and also some very recent articles published in high impact journals. Okay, so let's start our discussion, and here you will see that the concept will cover the depolymerization and recyclability. As I told that we will learn here that how the organometallic catalysts and metallocene catalysts are used for depolymerations. But before that, we have to understand why we need it. What is the importance? We are making, then we are breaking. So why it is needed? So this is nothing but called the recyclability of the polymers, and why it is needed. We'll discuss very shortly the methodologies of depolymerization which are available at this moment, although we will not discuss in more depth. And we'll just try to give a concept of circular economy and sustainable chemistry. This is very much important, as I told, very much important at this time. Okay, where in that age we are living now, because you know that we have the lifestyle has been improved a lot. Okay, and that's why we need a high energy demand. Okay, and for that high energy demand, we need fuels, we need new materials, and for that we have to have we have to use the circular economy, so that the same material is used and then again we can use the same material for same purpose or maybe different purpose, but which has the important purpose or which have the impact on the society. As example, if I give example like lithium ion batteries, now we are very much use the lithium ion batteries because that is one of the best batteries, and even in all the cases 90% electronic gadgets you will see that we are using the lithium ion batteries. Now if we use excess amount of lithium, okay, then after few years all the lithiums, okay, will be completed, okay, from, I mean, all will be used up, okay, because the source of the lithium in earth is limited, okay. So that's why we have to have the use the concept of the circular economy and the sustainable chemistry to continue a important technology or important material. So that concept I'll try to give you, and here we will be discussing the depolymerations. So we'll be more concentrated on that one, that strategy and mechanism of depolymerization, and then we'll discuss that how this organometallic and metallocene based catalysts can be used in this very fascinating but very important, okay, chemistry to solve this $1 million problem, okay. So these are the key words. Recyclability we will know, the metallocene, microscopic reversibility we will know, and depolymerations by chemical method, that is our main interest, okay, we will know in these classes. Now as I told that why we need depolymerations, okay. Okay, fine. In the very beginning of the class I showed the same diagram, and we were very excited to know that how this polyolefin, okay, or which is commonly called plastic, how it is has a big market, okay, and how the big scale it is produced because it is so popular. You cannot in the beginning I told that if you just think a single day without any polymer, okay, I am sure challenge you cannot, because the polymers is now so much involved in our daily life, we cannot really avoid the polymer. Now this is good, okay, we understand the polymer. Now it has also big effect. Anything if you use excess, okay, in a long run there will be big effect, okay. So big bad effect, okay. So I'll discuss all things, but here probably if you can recall that the plastic, okay, is in 1950 to 2020, okay, the it's almost around or more than 10 billion metric ton, okay, have been synthesized, manufactured. So you can understand how much, okay, polymers have been manufactured, okay, in this. If this trend continues, okay, then it is assumed that around 53 million metric ton will be synthesized per year, okay, by 2030, okay, is really big value. Now so much polymers are synthesized. Now what will happen after using it, okay, if there will be at some time that everywhere there will be unused polymers, polymeric materials, but what to do with this one, okay, and exactly this alarming situation is already started, okay, because if we all the used polymeric materials hardly, okay, the hardly 60 to 70%, okay, are used in landfilling, and only 10%, that is the maximum, is hardly used in for recycling purpose. So 10% is recycled, and you will see most of the polymers are actually are used for landfilling. That is really bad for the environment, because this is not a natural materials, these are synthetic materials, and we have already seen that the polymers like polyethylene, polyterephthalate, and all these polymers have really strong bonds, so it is really does not decompose or does not degrade spontaneously. Okay, so that is really a big threat to our society, to Earth, okay, or to human or to living systems. Okay, so one you see here that excess use of plastics. Okay, you will see that this is a photograph from the sea. Now it is so common even in India. Okay, you will see that so many plastic materials are even in the sea, and it is assumed that if it is continuous, that whole sea will be converted to a bin for the plastics if we are not careful on that one. And you know that that microplastics, okay, after partial decompositions, and these microplastics, okay, are now entered in food chain. Okay, the living systems of in the sea, they consume these microplastics, and then it entered into the fish, and that fish we consume, and you will see that this is a really big threat to the life or human life. Okay, and different type of very complicated disease like cancers are now very common for this kind of bad effect. So it's a really big threat. Okay, so it is very easily understandable from here that excess use of plastics has caused the excessive pollution in the earth. So one of the main reason of the pollution, environmental pollution, is the excessive use of plastic. Okay, apart from the emission of the toxic gas and other things. And as I told that landfill is around only 60 to 70, the landfill, most of the polymers are used for landfill, that is 60 to 70%, okay, and only 10% is used for resource generation. Resource generation means either it is used again to polymer or to other materials like fuels, and to solve partially the energy demand. So if we can convert to monomer, okay, or if you can convert or to the feedstock, okay, for valuable compounds, okay, or fuels, like fuels means like smaller alkanes, hexane, butane, heptane, that is really now high demand to make the valuable compounds, or to use as a feedstock from the used polymers. Okay, so that we'll try to learn in this class, that how it is possible, because this is very important not only for the industry, it is also important for the citizen, okay, who are using these materials, the polymeric materials, both. And also definitely the government encourages and have imposed various rules to protect the earth from the pollution caused by excessive use of the plastics. Okay, so I'm sure you are aware of that one. Okay, so you cannot really use now plastic bags as we used to do like the last 3 or 4 or 5 years. Okay, so in our government has also declared, okay, various rules about this against the excessive use of the plastics. Okay, so definitely we are the scientists, we are academicians or industry peoples. Okay, we will be now with this class we have also responsibility to develop or to think about that how these plastics can be reused, okay, to a valuable materials, and to stop the excess use of the plastics. As I told that you cannot avoid the polymers, because polymers is so much kind of a related to our life, but we should know to use in a restricted way. Okay, so here you will see that as I told that these are the ideal cases, that the polymers, like this is the monomers, and from the monomers we are getting the polymers. Okay, and then from the polymers we are getting the valuable compounds, okay, and the valuable materials, or the useful materials, and from the polymers we are getting the material, and then if we recover, okay, or then again if we recycle to polymers or to other materials, valuable materials, or to the same products, like here as I shown the pictures like tub, okay, chairs, all the domestic materials. If we can do that one, that the way we can actually reduce the use of the plastic to some extent, okay. And I'm sure that if any plastic material is nearby to you, I'm sure you have seen some kind of this kind of pictures, okay, like that one, okay. This is a triangle, that three arrows in a triangle shape, okay. We should all know that what is the meaning of that one, okay. This is a mandatory for any plastic materials, the manufacturer, this is a mandatory to show these symbols on the product, okay. I have already taken some pictures, okay, the materials which are available in my office. You will see that this is like it is written LDP, okay, the 4, okay. Here you will see the cycles, three arrows in a triangle, it is written as 5, and in below it is written PP. Here on the same thing you will see that 5 and PP, okay. And here you will see this is triangle shape, 3 arrows, and it is written 7, and in the below it is others, okay. And here also you will see PP. What is the meaning of that one? We should really understand, okay. And accordingly we have to think for recycling these materials. That is very, very important, as I told at this time, okay, we are living. So let's understand these symbols. So here it is, you will see that is it is called PET. We all know that this is basically terephthalate allied polymers, and you will see this can be recycled without any problem, okay. So this is recyclable, okay. And you will see this is HDP, okay. Here we put 3 arrows in a triangle shape, and it is written 2, okay, and 2 means this is HDPE, okay. So many cases products HDP can be written or cannot be written. If it is 2, you have to assume that this is actually high density polyethylene or related polymers. So this also you see this can be recyclable, okay. So PET can be, that is the recyclable, and the symbol is for PET 1 and 3 triangles, 3 arrows in a triangle shape. B stand for the PVC or vinyl related polymers, okay. So this is PVC or vinyl related or allied polymers. So here you will see that this is not recyclable, okay. This is difficult to recycle. So most of the PVC materials is actually not recycled. It is can be used for landfilling, but you cannot again use it and give a shape, okay. And this is, you see the LDP, the code is 4, okay. LDP is 4. This is can be recycled, but it is actually partially. Polypropylene, okay. You will see here most of the materials like plastic materials, you will see the PP, okay. These are all, you see that's order PP. Almost all the plastic the packaging materials used, which are hard, which like sanitizer bottles, okay, all the Dettol bottles, all these kind of bottles are actually made of polypropylene. So here also you will see this can be recycled, okay. 6 is for polystyrene. This is also again, it is not fully recycled, but can be done partially, can be recycled, okay. Fine. This tick means you can reform again the same material. So like if you are if it is a bottle, and you can make it again the similar kind of material like bottle or similar kind of materials, okay. So that is the fully recyclable. And the last one, that is the code is you see 7, that is the others. Others means this may be the acrylic plastics, okay, polycarbonates, nylons and others like, okay, which are not included in this PET, HDP, PVC, LDP, PP or other things. Okay, so this is depending, again as I told, that some are recyclable, okay, but not all the polymers are can be recycled, and this kind of symbols are mandatory for any manufacturer to put in the respective polymeric plastic materials. You can, if you can check with you, if you have any kind of plastic materials nearby you, you can check it. This is very important to know. Okay, now I am sure if I give one symbol, you can be able to tell that what kind of polymer it is and whether it will be recycled or not. Okay, you can check yourself. Okay, so another point I want to mention that here we know the two type of in the very beginning we have discussed that you can divide the polymers into two categories, okay, based on the response of on heating. One is the thermoplastic, and one is the thermosetting. Okay, I am sure that you can recall we have discussed already in our very earlier classes. Okay, so thermoplastics, actually what happens, if you heat it, it melts and softens, okay, and can be reformed, and thus it can be reformed okay when cooled. Fine, and that's why it is recyclable. Okay, fine. But thermosetting, what happens, this actually if you heat it, it hardens. So you can imagine that this cannot be recycled. However, it is by mechanical way, you can make it powder and then you can use it for filling purpose. Okay, so any thermoplastic polymers you can recycle, okay, without any problem. Okay, so this you should know that what kind of material it is, and that the way you can decide that whether it will be recyclable or not. Fine. Okay, so these are the common polymers used in daily life. Okay, this I already discussed in our previous classes. You will see that this is the basic structure of polycarbonate. This is the polyethylene oxide. This is, you will see that this is basically the PCP. This is the polyethylene. This is the nylon. Okay, 6,6 nylon, heavily used in textiles. These are the polysiloxanes. This is the PET. Okay, so you will see that this is a polyamide. Okay, so this is kind of similar to the nylon structure, and very special cases you will see that this is the polystyrene. This is all the polyethylene. Okay, different form of polyethylene, or you can more generic name the polyolefin. Okay, so the basic difference between these two categories, if I divide here, you can understand that here the left side, or like these are all hydrocarbon polymer. That means there is no heteroatom. Okay, all C and H, carbon and hydrogen, and the polymer skeleton has the saturated bonds. Okay, in the polystyrene, forget this benzene part. The skeleton I am telling, that is the saturated carbon. Okay, that is the 4 valency. Okay, and all are the polyalkane category. Okay. Now, in this case, the right hand side you will see that there the polymers with heteroatoms. Okay. So, you will see that is why the bonds are polar, and here it is non-polar. Okay. So, we will discuss after some time, okay, after few slides, that what is the impact, okay, of this polar and non-polar nature, okay, and how difficult it is to break a polar bond and non-polar bond having the polymers. Okay, that we will discuss after few slides. These are basically just to know to give an idea that these many polymers we used in daily life, okay, and heavily used for domestic purpose. Okay. Now, this is very important, okay, to understand now the circular economy and sustainability. Circular economy and sustainability is a kind of a very similar concept and heavily related concept. So, as I told that if you use one particular materials, okay, which has a limited source, and after some time what will happen, that resource will be stopped, resource will be exhausted, and then you don't have the resource to make the important materials, and then your product will not be very cost effective. So, we have to think a sustainable scenario to make the polymer or the material cost effective, so that it can be made without any much problem, and that is the concept is the circular economy. Okay, that means it is cycle should not be stopped. Okay. So, the three concepts of the sustainability is the efficiency, consistency, and the sufficiency. This is very important. Okay. The efficiency means it has to be very efficient method without investing much money. The process should be viable and it should not be highly cost effective. Okay. And consistency, so that means the method should be very effective method. Okay. This should be very effective. Okay. And the consistency, that again it is very much related to the efficiency, that it should be the process should be compatible with all in all time and with lower risk. Okay. So, this is very much like a similar as efficiency. Okay. And the third point is the sufficiency. That means it is basically the involves to reduce the waste generation. Okay. So that there is enough resource are available for the next batch of process. So, these three concepts are very much important to make a process viable and sustainable following a circular economy. Okay. So, the circular economy actually is regenerative by design and aims to keep products, components at all times in a cycle. Okay. So, most of the now industries follows the circular economy to make the process cheap, cost effective, and so that the common people can buy the material. Otherwise, it will be so expensive, nobody can buy it. Okay. And that is why the used polymeric materials, this is the high time to convert these used polymeric materials after use either to new products, okay, or to new plastic materials or the textile. These I am telling the used polymeric materials, or to use in the energy domain, the energy demand, okay, like to make the fuels. So these are the 4 domains, okay, are now peoples or scientists or industry peoples are jumping to contribute to these domains by converting the used polymeric materials for 2 purposes: to solve the demand of these valuable in these valuable domains, and also to reduce the plastic pollution. Okay, so this you see that how exciting it is and how important it is. Okay, so now these are, you will see, these are the some cyclic methodology. I will not go in very detail, but you just try to understand how it can be done. Okay, so you see that this is the refinery, and from the refinery we make the monomers like ethylene. Okay, let's, because we are in this course we will be more like involved in polyethylene, polyalkene, so ethylene or hexene, okay, for LLDP. So just consider like most of the monomers are basically from the refinery industries, are made from the refinery industries. So these are the monomers, and from the monomers we make the polymers, okay, by different methods we have already discussed. And then after processing we make the plastic products, and these plastic products goes to the consumer. And then what we do, okay, you will see the different materials after using it, and we throw it, okay, and this one, okay, now goes to the post consumer waste. Now time has come to recycle this one to again to useful materials, okay, and how to do it. So after collection and sorting to different type of materials, as example, like as I told that PP or HDP, okay, the symbols according to that one, okay, this one, the PT, HDP, LDP, PP. So according to that one you can sort it out, and after sorting, okay, if it is a thermoplastic, the route will be different. If it is other polymeric materials, route will be different. And also the how we are recycling, whether we will be using the for making the similar plastic products, or will be want to solve the problem of the fuel energy, or whether we will be making the monomers again. So that different recycling methods will be different strategy. Fine. So here you will see that this one, like here you will see this is the from the after sorting, if you do the mechanical recycling, you will come here the plastic products, okay, and then you will make again. So mostly like as I discussed already, like thermoplastic polymers, you can do it very easily. Okay, now another one you will see that yellow one, this is the primary recycling. So that means you can again make the polymers, and then you make the plastic products and then go to the consumer. Now this one, the gray one, that is the more challenging and more demanding, okay, challenging and more demanding. That is the you break the bonds. In other cases we are not breaking the bonds, here you are breaking the bonds, and you are making the monomer, and then from the monomer you are then again you can make the polymers, then plastic products, and then cycle goes on. And also from here you can also use the other materials, valuable materials like fuels as a byproducts or other new compounds. Okay, so these are very much important. This can be done by chemical recycling, that means by breaking the bonds. Okay, so these two are same. So this is and this is, okay, the blue one and the gray one, this can be done by the chemical recycling. This is very much challenging and very much demanding, and it is also the concept wise is really exciting. Okay, so in if you see this one, okay, this cycle, I just want to qualitatively I want to show once more that if it is when this is your monomer, okay, and from you are making the polymer, okay, and then you are doing the blending and forming, okay, so you are the applications, that is you are making all these materials, okay. Now what you can do, that you can do the, now from here you can do three ways. One is the this one, that is the primary recycling, okay. So this is called the primary by mechanical recycling, okay. And from here, if you can make the monomers or the feedstock, as example the fuels or other valuable products, okay. So that for that you need the depolymerations. In other cases you see that these are not depolymerization, these are basically mechanical recycling. Here we need the depolymerization, and that is, I told that it is a challenging, and for that you needs to break the bond. And how it can be done? This can be done by strategic design of the recycling methodology or strategy, okay, that we will be discussing. So you will see here that if this is the what are the depolymerization methodologies. So you can do by chemical, you can do primary, or you can do by mechanical. So this is the primary and mechanical is basically there is no involvement of the bond breaking process. These are chemical methods. We will be most interesting by following the strategy of the organometallic catalysts, and here you will see that this is the most demanding and most effective method, conceptualize and on the basis of the concept, this is very exciting. And others are like you will see that by ionic liquid, by metal oxide, by nanoparticles, by organocatalytic, those are also available, but those are not really very effective process, okay. And some of the polymers also it's biodegradable, okay, and various microbacteria actually are responsible to degrade, although these are not very effective methods, okay, but those you cannot also ignore, those are also good methods. But here we want to learn that how that organometallic catalysts, okay, which are used for the polymerization can also be used for depolymerations by choosing the right strategy, okay, that will be our aim, okay. So as I already discussed that what are the basic difference between these two category of polymers. This is the non-polar and this is the polar bonds, okay, and in general the non-polar bonds is very difficult to break the non-polar bonds, because you cannot really do any reactions with nucleophile or electrophile, because these are non-polar, and bond strength is quite high. If you see this one, see for like polyethylene, this is a model unit of a polyethylene. The carbon-carbon bond is, you see here, it is around 363 kilojoule per mole. So huge bond energy, okay. So and for model propylene, so it's very much similar, around 360 kilojoule per mole. This is like a polystyrene. You will see that again very strong bond. The Cc is around, Cc bond is 332 kilojoule per moles, and like polyvinyl chloride, you will see that carbon chloride bond is around 353 kilojoule per mole. Okay, so you will see that those bonds are very strong, very difficult to break the nonpolar bond because there is no center for electrophilic or nucleophilic attack. Similarly, the polar bonds, as example for carbonates or polyester, these are also quite high in energy. That is like you see 430 kilojoule per mole. The CO bond is around also 432. This one is around 342 kilojoule per mole. So this is quite high in energy. However, if you design any reagent to attack nucleophilic or electrophilic way, that can be cleaved. Okay, so that is so for that reason, that cleavage of the polar bond entity is easier than the non-polar entity. Okay, so you need a fine tuning of the catalyst or the breaking agent, and you can react with the non-polar bonds and you can break the bonds. Okay, one will discuss this thing in like here. If we see that R3CH bond, okay, we discussed in our previous classes that CH bond is a non-polar bond and how you cleave it. Okay, you by organometallic way. So you have to populate the electron density on CH sigma star bond. And how we can do it? This is called through agostic interaction, and this is called the CH bond activation. So we have to follow the CH bond activation or CC bond activation, okay, by transition metal chemistry. Okay, so that's why you need a very strategic way to break this non-polar carbon-carbon or carbon-hydrogen bonds in polyalkanes, and that's why it's very challenging and very difficult to depolymerize this kind of system. Okay, so in the next class we'll discuss very specifically about how to depolymerize, how to break the carbon-carbon or carbon-hydrogen bonds, and what are the strategies by the organometallic catalyst with a special focus with the Metallocene based catalyst, and to cleave the polyethylene or allied polymers. And as we have already learned that this process is very much important to save our earth and to save our environment, and not only for that, to make the polymerization process is viable and to maintain the circular economy. Thank you, and see you in the next class.